Welcome to the first of 3 videos that we're going to look at looking at equilibrium. When I think about equilibrium, the first thing I think of is the time that I lost mine, when I lost my balance. I could not stand up, I simply fell over. So when you hear the word equilibrium, think the word balance. Equilibrium is usually described in one of 2 ways, either static or dynamic, either still or moving. When we think about a static equilibrium, think of a seesaw. And if the people hold it still, then it is balanced. Or think about a 2-pan balance. When we think about a dynamic equilibrium, think about things going in opposite directions. And we'll look again and again at a simple equilibrium between 2 species, A and B. On the Moodle page, be sure that you go to the site that I've listed with the equilibrium simulation. It will help you understand this, so please go there. Again, all chemical equilibria are dynamic equilibria, 2 opposite processes occurring at the same rate. So we're back kind of our discussion of kinetics. Here's a simple example. Again, here is A, quote unquote, in equilibrium with B. So A is in equilibrium with B. We have a 2-step mechanism. A goes to B. That's the forward rate, is the forward rate constant, K sub F, times the concentration of A. And the backwards step is B going to A. So that's rate B is equal to K sub B times the concentration of the species B. Now, if we begin with only species A, then the rate starts rapidly and it decreases as the concentration of A decreases. The rate with regards to B starts at 0 and increases as B is formed. Now notice, at some point, the 2 rates are equal to each other. In other words, the rate in the forward direction is equal to the rate in the backwards direction. So that means that the rate constant in the forward direction times the concentration of A is equal to the rate constant of the backwards direction times the concentration of B. Now, when they are equal, we can rearrange that equation, and you get that the ratio of the forward to the backward rate constants is equal to the ratio of the concentration of B over the concentration of A, or products over reactants. Notice that's constant. We call this ratio KEQ, the equilibrium constant. We can extend this idea to any reaction or equilibrium. Here's a very generic reaction. A moles of A plus B moles of B are in equilibrium with C moles of C and D moles of D. We can write the equilibrium constant then as the concentration of C to the Cth power times the concentration of D to the Dth power divided by the concentration of species A to the coefficient Ath power times the concentration of B to the Bth power. Notice again, that's products over reactants. That's how we always form our equilibrium constant. Concentration of the products raised to their stoichiometric powers divided by the concentration of the reactants raised to their stoichiometric powers. This is called the law of mass action. Let's work 3 quick examples looking at these 3 equilibrium. The first one is nitrogen plus hydrogen makes ammonia. Notice that's 1N2 plus 3H2 make 2NH3. So our equilibrium constant is going to be the concentration of ammonia raised to the 2nd power divided by the concentration of nitrogen times the concentration of hydrogen raised to the 3rd power. That's a 3. So again, look, that's products over reactants, and everything is raised to their stoichiometric power. I didn't put a 1 by the concentration of N2 because when we learned our algebra, we know we don't put an exponent of 1. The next reaction is 1H2 plus 1Br2 makes 2HBr. Notice then that we've got the concentration of HBr to the second power divided by the concentration of H2 times the concentration of Br2. Once again, let's note that is products over reactants. And our third time here, we've got N2 plus O2 making 2NO. So my product is NO raised to the second power divided by the concentration of N2 times the concentration of O2. So every time, products over reactants. If we look at these three examples again, I've typed in the equilibrium constants there. Perhaps you can read them a little better than on the last slide. And I've also given you their experimental values at 25 degrees Celsius. We'll talk in our second video how we actually measure equilibrium constants, but for right now, just take these numbers because they're right. So if we look at N2 plus 3H2 to make 2NH3, notice that the equilibrium constant is a small number, 4.34 times 10 to the minus fourth. If we write that out as a decimal, we get 0.000434. That's a small number. Notice H2 to Br plus Br2 to make 2HBr is a huge number. 1.9 times 10 to the 19th. I'm not going to write that number out, but that's big. The last one, N2 plus O2 to make 2NO, has an extremely small value, 4.1 times 10 to the negative 31st. Now, let's think for just a moment and realize we're really glad that that one has a small equilibrium value because what's the air? It's nitrogen and oxygen. We don't want this reaction occurring at room temperature, and it doesn't occur much. So let's summarize there at the bottom. If KEQ is bigger than 1, that means we have a greater concentration of products and a lesser concentration of reactants at equilibrium, and we say the equilibrium lies to the right. What's on the right of the arrow? Products. So the equilibrium lies to the right. We get a lot of products, not much reactant left when we reach equilibrium. On the other side, if KEQ is less than 1, like the first one or the last example that we looked at, if KEQ is less than 1, then we have a lesser concentration of products and a greater concentration of reactants at equilibrium. And we say the equilibrium lies to the left. On the left side of the arrow are reactants. So in that case, the balance is far to the left. In our first case, if KEQ is 1, then our balance is to the right. Let's look again at this equilibrium between A and B. There again, so the equilibrium constant is just going to be the concentration of B divided by the concentration of A. And let's suppose that it has a value of 10 at room temperature. What that says is that at equilibrium, the concentration of B is going to be 10 times the concentration of A, because B over A is 10. Multiply both sides by A, B equals 10A. So again, in this case, equilibrium is greater than 1. The equilibrium lies to the right. If we were to start with 2.2 molar A, then we would argue most of the A will be gone at equilibrium. At equilibrium, the concentration of A would be 0.2. The concentration of B at equilibrium would be 2.0. And when we took B and divided by A, 2.0 divided by 0.2, we get 10, which is our equilibrium constant. The equilibrium constant is telling us where we will end up. Where is the point of balance? If I start with B as 3, so now I'm starting with only product. So now the equilibrium has got to swing back a little bit to the left, but not a lot because that ratio is still going to be 10. So very little B is converted back to A. And if we do the math, and we'll talk about that in the next video, at equilibrium, the equilibrium concentration of A is 0.27, and the equilibrium constant of B would then be 2.73. That's 3 minus 0.27. And the ratio then is, using those numbers, 10.1. And that's essentially 10. Now note, I didn't get exactly 10 because I rounded off the numbers. There's always going to be some round-off error when doing KEQ calculations. And an error of as much as 2 or 3% is not an issue for us. Now, there are some distinct properties of equilibrium, the equilibrium constants, KEQ, that we need to talk about. If we reverse the reaction, we invert KEQ. Now notice, here is our initial reaction, A in equilibrium with B. So again, my equilibrium constant, B divided by A. And we've said that's equal to 10. If I reverse the reaction, notice the equilibrium constant just gets flipped. What was on the top is now on the bottom, and what was on the bottom is now on the top. And so our value is also inverted. So the equilibrium constant for A goes to B is 10. The equilibrium constant using B as our reactant and A as our product is 1 over 10, or 1/10. So that's the first property. Our second important property of KEQ is if I multiply the reaction by some number n, then I'm going to raise the value of KEQ to that nth power. Again, there's my initial reaction. One more time. KEQ, B over A, is 10. If I multiply that by 2, so 2A goes to 2B, my KEQ becomes B squared over A squared, products over reactants, raised to their proper power. And let's notice that is just B over A squared. So my equilibrium constant is now 10 squared, or 100. So when I multiply a reaction by a number n, I raise the value of the equilibrium constant to that nth power. The third property, and a very important one, one that we'll see again and again, is if I add two reactions, I'm going to multiply their equilibrium constants. Here again, reaction 1 is A in equilibrium with B, and we've said one more time, that's 10. Here's a second reaction. B is in equilibrium with 2C. So the equilibrium constant there would be the concentration of C squared divided by the concentration of B. That's products over reactants for that reaction. And we're just going to assume, we're just taking that equilibrium constant, is 0.5. Notice now when I add these two together, so now we're just going to treat them like math, and we'll cancel out the B's, and we're left with A is in equilibrium with two C's. The equilibrium constant for that is going to be C squared over A, and we note that that is the first equilibrium constant times the second equilibrium constant. Again, let's notice when I do the math, the B's cancel. I would then multiply the two equilibrium constants because B over A is 10 and C squared over B is 0.5. 10 times 0.5 is 5, and we've multiplied those constants. Very often when we're talking about gas phase reactions, rather than using concentrations, we'll use pressures. All of the equilibrium constants that we've looked at before this slide, we used KEQ, and those were KCs, a concentration-based equilibrium constant. Kp, the pressure-based constant, uses the same form. It's still products over reactants, but rather than using concentrations, we'll use partial pressures. So let's note, here are my three reactions again. N2 plus 3H2 are in equilibrium with 2NH3, and it's still products over reactants. But again, let's notice, however, that now we're going to be using partial pressures rather than concentrations. So again, it's still products over reactants. This is products over reactants. And this is products over reactants. However, this time, because everything is a gas, it just makes our math easier to use pressures rather than concentrations, because that's how we measure the amount of gas, by its pressure. Now let's notice, however, that the numeric values of Kp and Kc are going to be different. So you'll need to note when you read a problem, or whether when you're reading an article or reading a book and they talk about the equilibrium constant, you need to know what are they referring to, Kp or Kc, when we're dealing with a gas phase equilibria. Please also note that when we are doing this, these partial pressures are going to be in atmospheres. It can be done. We're not going to cover it today. Numerical values, I can go back and forth. I can calculate Kc if I know Kp. I can calculate Kp if I know Kc by simply substituting using the ideal gas law. The last thing we want to talk about in this introductory video is an equilibrium constant for a heterogeneous reaction, one where we have more than one phase present. We might have gases and we might have aqueous species. We might have gases, we might have liquids, we might have solids. We might have all of those present. And we need to have a generic way of expressing the equilibrium constant for these heterogeneous reactions. The rules are simple. Number one, my gases are going to appear as partial pressures. My aqueous species are going to appear as molar concentrations, just like we've seen before. The big change here is when we have a pure solid or a pure liquid, they do not change their molar densities. The moles per liter for liquid water is the same. Doesn't matter whether I've got a drop or a gallon. The moles per liter, the density of a solid like sugar, doesn't change. Doesn't matter whether I have a teaspoon at the bottom of the glass or a cup of sugar at the bottom of the glass. So those pure liquids and pure solids do not appear in KEQ. Let's look at three examples quickly. Here's one for solid mercury 2 oxide. If I heat it, it will decompose into liquid mercury and oxygen gas. So notice on our KEQ is going to be the partial pressure of oxygen. This is a pure liquid. Its concentration is going to be constant. This is a pure solid. Its concentration is going to be constant. And we simply put in a 1. So the equilibrium constant for this reaction is going to be the pressure of O2 times 1 divided by 1, or simply the pressure of O2. Here's the reaction for hydrogen gas plus oxygen gas reacting to form liquid water. My only product is a pure liquid. So on the top for my products, I just put a 1. Both of my reactants are gases, so they go in as partial pressures. Partial pressure of hydrogen gas to the second power times the partial pressure of oxygen to the first power. So that KEQ is going to be 1 divided by the partial pressure of hydrogen squared times the partial pressure of oxygen. Our last example is the reaction of CO2 dissolving in water to form carbonic acid. Again, do a little nomenclature here. This is, carbonic acid. C-A-R-B-O-N-I-C. You can't read it, but there it is. Carbonic acid. Notice my only product is an aqueous species, so I have the concentration of H2CO3. My reactants are gaseous CO2 and a pure liquid. And again, point 3 up top, pure liquids don't appear. They just have a contribution of 1. So CO2 appears as its partial pressure. So the equilibrium constant here is going to be the concentration of carbonic acid, moles per liter, divided by the pressure of CO2 in atmospheres. This concludes our introduction to equilibrium. Our next video will talk about how we measure equilibrium constants and how we can use them to measure equilibrium conditions.